Please give heading in the notes, common probability distributions. So to many, this is where the true statistics actually start, because this is where you would learn how to make use of the probability distributions. Now, since we have a lot of non-commerce, non-engineering background people here in the class, commerce background or non-mathematics, I'm going to go initially slow extremely, and then depending on how you're picking up, the speed would be adjusted. So, first example, think of a six-sided dice. Okay, you decided that you want to start throwing these dices. So, which are the possible outcomes you can get? You can either get 1, or you can get 2 or 3 or 4 or 5 or 6. What is the probability of getting 1? 1 by 6. And what would be probability of getting 2? 1 by 6 and 3 and 4 and 5 and 6. So this is the simplest example of probability distribution. So just by looking at this graph, you get a sense of where the data is and what is the frequency of data. A more complex version could be somewhat like this. Imagine if you have a probability distribution in this fashion, or imagine if you have a probability distribution like this. Now these are also probability distribution, and if you remember, this is somewhat similar to normal distribution, and this appears to be a skewed distribution. So by looking at this, it gives you a sense of maybe there is a high frequency of data that's here. That means there is a very high probability in the center, and then there is less probability in the tails. Are we clear with this? So you write down the first example. You can say probability distribution of possible outcomes of throwing a dice. Or just say dice and make the probability distribution. Assuming you're done with this, now this area that I'm covering now, that is in one of the subsequent learning outcomes, but it makes sense to do it now. So I want you to divide your page into 4 parts, and we are going to look at 4 different types of distribution: discrete, uniform, discrete, non-uniform, continuous, uniform, continuous, non-uniform. So we are looking at 4 different varieties of probability distributions. Now, discrete means the data set is discrete. It is, I finished writing this. Discrete means the data set is discrete. It is not continuous. So we did a few examples in the previous session. We said number of people sitting in this class. We can have either 60 or 65, 66, 67. We cannot have 65.25. Can we, Mahavir? No. So because we cannot have this, we have a limited number of range, or we have this data set to be discrete. Are you following what I'm trying to say here? But imagine we are looking at weight of an individual. It could be 60 kg or 60.00001 kg, right? And then it can be infinite number of values. So then that type of data is referred to as continuous. So then depending on what data set you're looking at, it would either be a discrete data set or a continuous data set. Let's say the returns earned on a particular stock. Will that be discrete or continuous? Continuous. Number of days taken to finish CFA level 1 syllabus. Discrete, assuming we count them as full days. Then average amount of rainfall in a particular day. Continuous. So if you are looking at discrete data versus continuous data, that's how we have the distribution at the top or bottom. Uniform means probability of every outcome is same. Uniform simply means same. So the example that we did, throwing of dice, probability of every outcome was 1 by 6. Are you following this? but at times the probability of outcome would not be same, then those data set would be referred to as non-uniform. So discrete uniform, discrete non-uniform, continuous uniform, continuous non-uniform. Let's do example of each one of them. The first one we've already done, the probability possible outcomes when you throw a dice. So we know that 1, 2, 3, 4, 5, 6 and probability of each one of them was 1 by 6. Then we would look at discrete non-uniform. So let us say average number of students attending a class, average or number of students attending a particular class. Okay, so the range might start from 0 and let us say the maximum number of students in that particular school is 100. Now on an average you would see that there would be maybe a very high frequency around 90, because on a single day there would be a few people not present in the class, but there would be very less frequency around this region. So ignore the scales, okay, ignoring the sales. So you will have extremely high frequency in the range of 90, and then maybe some frequency around 80, some frequency around 70, some frequency here is 100, and then it will very rarely happen that there are only 10 or 20 people attending a class. Okay, so then we have a distribution here. It is still discrete, but now it is a non-uniform distribution. Is that making sense? Yes, no? Now continuous non-uniform. So this is where you would be spending most of your remaining time on statistics. Most of the distributions that we would be looking at, they would be continuous, they would be non-uniform. So a simplest example here is normal distribution. Okay, have you seen some characteristics, normal distribution? No? Okay, so we'll see that later on. But a normal distribution would be a perfect example of continuous and non-uniform. So this is a probability distribution. Your center value is here where there is a very high probability, but in the tails here on the left and in the right there is very less probability. And a continuous uniform distribution example would be probability of having a puncture on a car tire. Okay, so think of it to the best of my skills. So we have a car tire like this. Will you agree that every region has an equal probability of being punctured? Correct? You can have puncture at any surface area there. So that is a uniform distribution. And it is continuous because will you also agree that there are infinite number of points on a tire where we can have a puncture? So if I pinpoint specifically one single point, okay, and if I ask you what is the probability of having a puncture there, you would say it's almost impossible because there are infinite number of points there. So you cannot have probability of one single point, but you can have probability of a region. In terms of graph, a continuous uniform distribution will look like this. That probability of every region is same. There is equally likely probability that the region of the same size will have the same probability of getting punctured. Are we okay? So please write down. So the look on your faces right now is not very inspiring. Have you understood this or you want me to repeat again? How many of you want me to repeat? Continuous, non-uniform. It could be anything. So most of the distributions in real life would be, or many of the distributions in real life would be continuous, non-uniform. Think of average returns earned on a stock. So maybe certain stocks will on an average give you a return of 12%. Okay, so what is the probability of having a return of 12%? That's a very high probability here. Then at times the stocks might go to the extent of also giving you return of minus 30%. or they go to the extent of giving you returns of, they will go to the extent of giving you return of, is that distance same? This is 42, this is 42. So they will go to the extent of giving you very large returns as well, but probability of having very large return is less, probability of having very large negative return is less. There is a high probability that your returns would be in the range of 12%. Are you following this? So then why is it continuous? Because you can have 12% or you can have 12.001, 12.002. So there are infinite number of range on the x-axis. Are you following this? And then if I ask you what is the probability of having exactly 12% return, that answer will always be 0. Because when you're dealing with a continuous distribution, you cannot have probability of a particular point. But if I ask you what is the probability of having a return between 12% to 14%, then you would say fine, so we are looking at probability of maybe this range, and then you can estimate what is the probability of having a return between this number. So the trick is, on a continuous distribution, probability of a single point is always 0 because we are looking at infinite possible times. Easiest way to think in the context of tire example. If I show you a point and ask you what is the probability of having puncture here, that's infinite, 1 divided by infinity, because there are infinite number of points. So we can never have probability of a single point. We can always have probability for a range. Are we okay with this? So we'll do some example. The x defined as this, we'll do the same example there. 1, 2, 3, 4. This is how you define your data set. Now probability of x is given to you as x divided by 10. Now why 10? Because the total of these numbers is 3 plus 3 is 6 plus 4, 10. So if I ask you what is the probability of x, and additional data is, this is now a discrete distribution. So what is the probability of x? You would say 1 divided by 10. So what is the probability of 1? Probability of 1 would be 1 divided by 10. What is the probability of 2? It would be 2 divided by 10. What is the probability of 3? 3 by 10. And what would be probability of 4? 4 by 10, because that's how your probability function is being defined. Now there is also called as cumulative distribution function. Going forward, I am going to simply call this as CDF. Okay. We typically denote that as the f of x. So when we say f of x, we actually are referring to the cumulative probabilities. So here f of 1 would be 1 by 10. F of 2 would be 1 by 10 plus 2 by 10. F of 3 would be 1 by 10 plus 2 by 10 plus 3 by 10, and then f of 4 here would be 100%, which is 1 by 10 plus 2 by 10 plus 3 by 10. Let me be more explicit. 1 by 10 plus 2 by 10 plus 3 by 10 plus 4 by 10. So what is the probability of having a number less than 4? 100%. But what is the probability of getting a number less than 3? So cumulative. What is the probability of having a number less than 3? So how much is this? 60%. Probability of having a number less than 2? 40%. No, 30%, and then 10%. Is that alright? So write down this. Let's do one more example. So now on the exam, they might give you a probability function, and then they will ask you to check whether the probability function is defined correctly. Okay, it's very unlikely they will ask you questions on this segment, but your thought process should be clear that P of x should be defined in such a way that your total probability of all possible outcomes should always come out to be 100%. Otherwise your P of x is not defined correctly. So here this is 10%, this is 20%, this is 30%, and this is 40%. So total had to come to 100. If the total was not to come to 100, then you have not defined the probability function correctly, and then the question might just ask you that is the probability function defined correctly, yes or no. Okay, so again the same logic that we learned in the previous session. Probability will always be between 0 and 1 and total of all the probabilities has to be 100%. We'll do one more example. Let us say x is being defined as 7, 12, 20, 50 into 0.5x, and then you have to decide, number one, whether probability of x is being defined correctly. Second, find out probability of 23 and find out f of 23, p of 23, f of 23, and p of 23, 23%. So step number one, you might as well calculate probability of 7, 12, 20, 23 and 38. This will come out to be 7%, 100%. And then what would be the f of 23? So you take total of these values, which would come out to be 62%. Okay, this is how these probability functions look like. So when you're looking at the probability density function, okay, so what it means is it gives you what is the, if you want to know what is the probability on the left of -1, then you would take this entire distribution which is under that area. When you're looking at cumulative distribution function, then what is the probability on the left of -1? Just by looking at this point, it will give you the cumulative probability. If you want to look at what is the probability on the left of +1, you just look at this point and it will give you the probability. By following the difference, because it is giving you the cumulative distribution, whereas this was just giving you the probability of that region. I don't know if I'm making sense here. So if you are looking at what probability we have on the left of -1, you will have to measure this probability. But in this distribution, if I ask you what is the probability on the left of -1, you just have to look at this probability because it is already cumulative, discrete uniform distribution. Let us say now your x is defined as 1, 3, 5, 7 and 12. Additional information that I give you is that it is a discrete uniform distribution. Discrete uniform distribution. So the moment you know it's a discrete uniform distribution, you can yourself define the probability of x. So how many values do we have? 1, 2, 3, 4, 5. So probability of any x is going to be simply 1 by 5. So which means probability of 1 is going to be 1 by 5. Probability of 3 is going to be 3 by 5. Probability of 7 is, I'm so sorry, I should have said 1 by 5. Probability of 7 is 1 by 5. Did I miss something? Oh, this was 5. 7 would also be 1 by 5 and 12 would also be 1 by 5. What would be probability of 14? 0. What would be probability of 8? 0. What is the probability of 0? 0. Because they are not a part of your distribution. What would be f of 12? 100%. What would be f of 7? 80%. F of 3 would be 40%. Do you want me to repeat this again? So it is discrete but it is uniform, and uniform means every outcome has a equally likely chance or equally likely probability. So 5 variables, that's why 1 by 5, and then probability of each of the variable is 1 by 5, which is a part of distribution. If it is not a part of distribution, then that will simply become 0, and f of this would be simply the cumulative probabilities. Assuming you're okay with this.